Okay, so what we're going to do now is we're going to look at this problem and look at a momentum balance. So if you were to think about mass flow, as you saw here, as rho times u, then integrated over a length as opposed to an area, it's really a mass flow rate per meter per second. Well, we're going to have the same issue when we integrate momentum, and it really is it's an integration of momentum flux. So it's going to be rho u times u normally. So let's do that over each of these boundaries. There, 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 and there. Okay, so go over to derive values, right click, hit integration, line integrate. You will change the name and we'll call it inlet momentum. We'll hit OK. Then we'll make sure we pick the right boundary. Excuse me. Add that. We're going to go from what would you say? Just the velocity alone. Of course, you can see meters squared per second, but that's because we've integrated. They imagine that you've integrated velocity over the length. Hence, that's why you'd have the meter squared. So if you go over and just look again at mass flow, you've got to make sure that you get the right density into this momentum equation. So it's this times u times u. Okay, and it will fix the units automatically. And so we've got rho times u times u. And if you think about this, this would actually be a unit of mass flux, or force per unit length. So let's do evaluate it. And there it is, a force per unit length, Newton per meter. Hold on to that value. Now let's go to the outlet momentum. We'll do another integration. I guess we can just hit duplicate. And we'll change this so that it's outlet momentum. Erase the 1. Pull that out. Go to the outlet. Since this is the plate surface right here, we'll add that boundary 4. And we'll do the same expression. And we evaluate it. Ready? Set. I think I have everything right. Evaluate. Okay, so it had an outlet momentum of this and an inlet momentum of that. What's happening? Well, there's obviously some forces applied, but we also should be careful about another momentum loss, which is along this boundary. So we're going to do duplicate again, rename, do outlet momentum top. We're going to go up here. Now this is going to be a little bit more complicated. It's actually going to be a component of the velocity, first of all, that travels through the boundary, and then the x component of it at that boundary. So this is basically the effect of carrying x momentum out through a vertical surface, and that's why this expression is changed. The key idea, though, is to pick the right boundary, which is this one, boundary 3. So this is the expression. It's in the right units. We hit evaluate. Okay, it's a very small unit of momentum flux. What we need to now do, based on the Reynolds transport theorem, is balance the change in momentum flux with the net external forces. So those external forces are derived from either viscous or normal forces. So what we need to do is calculate the viscous shear here. And so what we want to do is do another integration, line integration, rename viscous shear, and that'll be a force per unit length as well. We'll have to pick the right viscous shear area, which is obviously the wall where there's a no slip condition. We'll come down in here, and I believe there's a standard expression. Shear, total stress, viscous stress, and it's in the x direction, and it is in a newtons per meter. So we've got that, and which direction is this acting? If the flow is coming in at this boundary and exiting that side, yes, the viscous shear actually acts to push the liquid in the opposite direction it's flowing. So it's an opposing force on the plate, on the fluid as the fluid goes across it. So I believe we have everything right. We have the right boundary, we have the right expression, and obviously the right units. So we'll hit evaluate that. That's the negative value. So let's see. Yep. Okay, so you can get all the different values. Good, I guess, the different tables. And then finally, let's look at pressure forces. So this is, let's say, duplicate, change the name, pressure inlet. So we'll get rid of that. There's a pressure force on the inlet. We add that. We'll erase that. Go into laminar flow. Go to, what is it, pressure. And that'll be integrated over a distance. So obviously it's going to be newtons per meter as a result of that integration. Yeah, so we'll do that. Pressure inlet. Great. Evaluate. Then we'll do pressure. Sorry, let's duplicate this again. Rename. We're almost done. At the very end, we'll sum up all these forces and calculate what the difference is between those forces and the net momentum flux. So we'll first of all get rid of that because that's not the inlet. I'm sorry, it's not the outlet. This is the outlet. We'll integrate and evaluate. Right, so that was a boundary condition. We'll look at the top. Let's see, that pressure that would be acting normal, which isn't in the x direction. We probably should look at the viscous shear, though, at the top. Duplicate. Rename. Viscous shear top. And we'll remove that, but add this one. Add. It is the viscous shear. Got the right boundary, the right units, and we'll evaluate it. Wow, very small value. So, if you take the viscous shear stress with the correct signs in each case, shear stress is acting in the negative direction. The pressure is acting in the positive direction. This viscous shear at the top is acting in the negative direction. If you combine all of those forces and compare them to the inlet momentum, I should say the net sum of all of these momentums in the x direction. So when you go to Reynolds transport theorem, that's in your textbook, the inlet momentum, because it's opposing the normal, is considered a negative momentum. The outlet is considered a positive momentum. So both of these outlets would be positive momentums. when you sum this number and this number, the outlet values, minus the inlet value, it should equal this viscous shear and pressure shear summation. I hope that's been helpful. This is a classic test to make sure that a numerical solution involving fluid mechanics is correct. Obviously, Newton's law cannot be wrong, or else there's something wrong with your code.